Hello everyone, today we'll be going over why generalized geography is PSPACE complete. Let's move on. So first of all, we need to define what generalized geography is. It is a common party game where every next player has to guess a city name that starts with the last alphabet of the previous city. So for example, we have Cairo ends with O, then Oslo that starts with A, ends with O, then Osaka that starts with O, ends with A, and then Austin that starts with A. So let's look at creating a graph model. So we can simply create a graph model using all of these cities as nodes, where the city that ends with A will be connected to the city that starts with A.
All right, so since we're in the domain of computer science, we can generalize the graph we just showed you by creating another graph that looks a little bit like this. So this is simply an arbitrary directed graph, and we can start playing the game of generalized graph geography here in this manner. So a player selects a vertex, and then the second player selects a vertex, and then the first player selects a vertex, and then so on until a path is created. And the person that ends up being stuck loses, and the other person wins. So essentially, this graph game that we are playing is a decision problem. And the problem here is to determine whether there is a winning strategy for a given graph using the rules that I just stated. And we can show that the generalized geography problem is p-space complete by first, and we will first show you that it is p-space hard. So we can recall that to show that a problem is p-space hard, we need to reduce a known p-space hard problem to it. And the problem that we've selected here is true quantifiable Boolean formula. And suppose we have a truly quantifiable Boolean formula of this form, where we have a couple of conditional quantifiers and one universal quantifier. And using this formula, we can do the reduction by creating a graph, and the process will look a little bit like this. So first of all, for individual variables, we create two choices, true or false, by assigning variables xi or not xi. And we will assign roles to each player. So player one will choose existential quantified variables only, and player two will choose only universally quantified variables. And the game works in such a way that both players make their choice of variables and keep doing so at each turn until all the variables are exhausted, and then the graph reaches to the clause stage, at which stage all the variables are now checked and are fed to the clauses, and all the clauses are checked. And depending on whether the clauses are satisfied or not, the path will be directed to a terminal, and a win or lose will be assigned. So this is how it will look in diagrammic form. B is the starting point of the game. Each individual variable will be selected until all the variables are exhausted, and the game will then move on to C, where each individual clause will be checked, where the clauses are represented by C1, C2, and Cn, and a win or lose will be assigned. And this reduction is correct because a winning strategy for player one will correspond to a satisfiable assignment for the true quantified Boolean formula. And if such an assignment does not exist, only in such a condition will player two win. So let's analyze the time and space complexities for this now.
So let's look at space complexity. First of all, for the sake of simplicity, our graph will be represented in the form of adjacency list. So first we'll talk about how much space the representation of our game or graph takes. It only depends on the number of vertices and edges, where vertices will be depending on the number of variable and clauses in the TQBF formula, and E can be quadratic in the worst case. Now let's look at space required for storing our game states. We have to remember the path or the number of nodes that the player have gone through. The sequence or path can be as long as the total number of variables and clauses in the original logical formula. Therefore, the space needed to store this path grows linearly with the size of the formula. Now let's look at how much space would be required to store the algorithm or the logic behind this game. So this will basically be a depth first search, where a player will be moved from where player will move from one node to another depending on the logic of the game. However, the space this will take will only be O n plus m, where n is the number of variables and m is the number of clauses. Now let's look at the time complexity of this. So iterating through the TQBF formula and creating the appropriate graph based on our definition will only take linear time, which depends on the number of vertices plus the number of edges. However, playing game in the worst case can take at least O of vertices multiplied by clause. This depends because the variables, because V depends on the number of variables or the number of turns that each player will take. Meanwhile, the C determines how complex each problem is or how many different routes a player can take. Now, to sum it up, we have successfully shown that generalized geography problem is in fact p-space complete because G is in fact in p-space, and we have reduced a known to QBF problem to our generalized geography problem. We have seen that this means that given a graph, we can determine a winning strategy without needing an exponential amount of memory, and also that any instance of TQBF can be transformed into an equivalent instance of GG. This will be all for our presentation. Thank you.